Well, thank you all for getting back. I know it's a long day, but you're not going to want to miss the afternoon session here. We have Dr. Lee Orff from the, and I'm going to make sure I have this right, SIMS. That's the way meteorologists know it, but it's the Cooperative Institute for Meteorological Satellite Systems, which of course the University of Wisconsin is a big part of, because it's basically where satellite meteorology had begun way back in the 1960s. So a lot of what you guys see on the weather satellites that we show on the news, a lot of that stuff just started right here in Madison. But Dr. Orff is going to give a presentation that I've seen bits and pieces of it. I can't wait to see the rest of it. But this is 3D modeling of severe weather storms. So, you know, we show you the fancy maps on the TVs. We put arrows and cold fronts and warm fronts and that stuff. But most people think of meteorology as kind of being in 2 dimensions, you know, flat weather maps. Well, this takes it into the 3rd dimension and actually be able to visualize storms and how tornadoes develop in storms, where they develop. And this is crucial for weather spotters to understand, so it gives them a better idea of where you might expect severe weather, things that you might want to look for, depending on what the weather conditions are. So, without much further ado, I will present Dr. Lee Orff, and hopefully if our sound gentleman is here, you can turn your microphone on too. Oh, there you go. Hey,
all right,
there
excellent. We go. Thank you, Gary.
You're welcome.
Thanks all of you for coming out. It's a real treat to share my research with the rest of the world. Ask any scientist, and they'll tell you they love talking about their research. My research happens to be on tornadoes and supercell thunderstorms. And so I'd like to thank Matt Lazzara for inviting me and everyone else who's been involved in this spotter gathering, as you could say. It's a very important thing you guys do. So I'm going to talk to you today a little bit about some background on supercell thunderstorms. I don't assume anybody knows everything about them. I'm just like, nobody knows everything about them, but I'd like to give some preliminary material, talk about why we study them. I don't probably have to explain that too much for you folks. And look at the different ways we study supercells, because a lot of supercell research is indeed going out in the field, taking data, scanning with radars, or taking in situ data with instrumentation. But that's not the only way. There's other ways we can study these storms that really complement observational studies. I'll talk about the different ways we observe and then talk about models, and specifically about half of my talk is going to be animations, visualizations from a 3-dimensional simulation I did on a supercomputer that produces a long track EF5 tornado. And this has been sort of a pretty exciting result for me because it's something that really hasn't been done in the past. So what makes a thunderstorm a supercell? Okay, you go outside on a day like today, maybe in a month from now or so, you'll see cells popping up here and there, but we generally don't have thunderstorms producing tornadoes very frequently, which is probably good. So most thunderstorms are called airmass thunderstorms, or just think of them as ordinary thunderstorms. They last about 45 minutes. You see clouds growing like cauliflowers spraying up. You see rain and hail, lightning and thunder, some winds, and then it all collapses and it's over. So you can go, and the internet's a wonderful thing. You can find all sorts of lovely pictures. I like this one. It's a nice example of an airmass storm. You can see distinguishing features include this anvil, so you can think of a lot of air going upwards and it's encountering a boundary called the tropopause, or the upper part of the troposphere. It sort of acts sort of like a spring, pushes things back down at you, so it kind of comes up and spreads out. It's kind of like upside down if you were to dump some water on the table, right? And you'll also notice it's if you're starting to see precipitation here, this is in the mature phase of the storm, so it's beginning to collapse. It's the beginning of the end. It will produce some rain, and in half an hour, you'll probably just see some remnant cirrus clouds as it dissipates. Now, some ordinary air mass storms produce damaging winds. This is a nice photograph of a downburst producing thunderstorm. So this is another ordinary thunderstorm. This is in the supercell. It's in a very low shear environment, low K, all the indicators we look for. But it is producing, these storms can produce damaging winds. So here we have the storm collapsing again. This is rain and perhaps a little bit of graupel or hail. But what you really notice here are these features on the side. And this is dust and dirt being kicked up from this very strong downdraft, impinges the ground, and then spreads out, kind of like dumping water on the counter I mentioned earlier. And this feature is often called a roll vortex. You tend to have this horizontal ring of air that rapidly rotates. It's kind of like a tornado on its side, but not really. You can sort of think of it that way. And you also can see some pretty strong winds in these. So I did my PhD thesis here at UW Madison on downbursts. So I gotta put it in. So again, schematically, this was all the result of what's called the Thunderstorm project, which was shortly after World War II, right about when radar was being developed for operational purposes or for meteorological purposes. Basically, one of the major outcomes was that thunderstorms tend to have 3 different phases. The towering cumulus phase, where it's beginning, the mature stage, where you see strong updrafts sort of collapsing into downdrafts, and the dissipating stage, which is dominated by downward motion, drying, and dissipation of the cloud. Okay, that's just an ordinary thunderstorm. What about a supercell? Supercells are a little different. They still have some of the same features of air mass thunderstorms and how sometimes they're initiated, you still have warm waste air rising, usually some other things, but supercells occur in specific environments that don't happen all that often, but when they do, they provide a potential for some very, very severe weather. So when you start to sort of look at a supercell, what are the characteristic features? You see a rotating updraft that is persistent, lasts a long time. Supercell thunderstorms can last several hours. Think of the tri-state tornado, just keeps on going. Persistent rotating updraft, a single one, and on they go. So this little sequence shows pretty nicely some time-lapse photography of a supercell. So one thing you notice is the rotation. If you look at how the storm is rotating, that is indicative of a supercell. Notice how you sort of have this giant rotating wall cloud. This is what's called the forward flank of the storm. A lot of precipitation is being produced here, rain and hail. And you can see how some of it's kind of scooting inward towards this big monster updraft. So there's a very strong updraft in this storm, and it is responsible for lifting lots of air and causing lots of wind shear, and it's an important aspect of maintaining a long track tornado or a strong tornado. You can see how the dust is being kicked up here, and you're lowering in the cloud here, something that looks like a little tornado maybe forming. And anyway, so that's a supercell. That's a little bit different than an air mass thunderstorm. But most of you, again, know this. You're being trained to understand these features of supercells. So here's a schematic. I noticed you have a poster out front as well that gives you kind of a breakdown of what's going on inside these storms. As a researcher, I'm interested in what's going on inside the storm. Videography is very important. It is an important part of meteorology, but you can't see into the cloud very well, especially if there's a lot of rain. You can't see even the tornado. So here's the schematic showing you the rotating updraft. It's the mesocyclone. We break this storm into pieces, into flanks, you could say, the forward flank in the direction it's going. This is the forward flank downdraft region of the storm, the rear flank downdraft region of the storm. These two sort of downdrafts sort of form boundaries, and those boundaries intersect. And right around this point where they intersect is typically where we see tornadoes form. So just an overview of supercells to distinguish them from ordinary thunderstorms. So this is the type of storm that I'm studying. And whereas you can get tornadoes and damaging winds from ordinary thunderstorms, or maybe multi-cellular thunderstorms, bow echoes, non-tornadic strength winds, when it comes to the really, really devastating tornadoes, so we're talking Joplin, Tuscaloosa, Plainfield, Illinois, one of the ones that's in my mind because it happened not too far from where I grew up, that was in 1980. Those types of storms are always supercells. You don't get a DF5 wedge tornado from an air mass thunderstorm. So you can say pretty confidently that the strongest tornadoes are always caused by supercells. So they also produce just flooding and hail and other things that cause damage. So we clearly want to understand them. Obviously, in weather, forecasting is a very important component of weather. It's one of the main charges of the Weather Service to issue warnings and watches to keep people out of harm's way. In order for us to get to the point where we want to be regarding forecasting, we have to understand what we're trying to forecast, right? It makes sense to just understand the features. So my view of things is that there's enough to learn just on supercells and tornadoes in the research realm. Once we understand that better and start to understand the features that cause tornadoes and cause tornadoes to last a long time, then we can sort of hopefully push that research into the operational world so that better forecasts can be made, fewer false alarms, and more targeted warnings. So that is the goal. And you get different numbers, but about 1 in 5 of supercells produce tornadoes, so it's not good enough to see it as a cyclone, so it's going to be a tornado. If we issued warnings like that, the public would never listen to anything we said. So there's certain distinguishing features on radar that can indicate tornadogenesis, but they're not very good either. You really want to be able to see, to know what tornado is going to form before it forms, and we haven't gotten there yet. And only 1% of tornadoes out of the 20% of tornadoes from supercells are in the EF4, EF5 range. So we're talking about the most rare type of tornado, but the most damaging. And yeah, it's about 90%. I talked to Harold Brooks, who's a tornado climatologist in Oklahoma, and he said that about 90% of the fatalities in all tornadic storms comes from EF4s, EF5s, so top of the line. We may get a handful of those a year. Some years we don't even get F5, EF5 strength tornadoes. But these are the ones, because they're so persistent, they generally are large, they generally go, some of them are on the ground for a long time, they will produce the most fatalities. So there's a lot of there's a public reason for the general betterment of society type of thing to argue for studying these things. And unfortunately, we don't know why some supercells produce no tornadoes versus weak tornadoes versus monster EF5 wedges or whatnot. This is like really what we're aiming for. Once we can sort of look at multiple supercells, whether it's observationally, theoretically, or using models, we do enough of these things and we start to pick apart what makes these storms different. Then maybe someday, when there's an outbreak or a storm pops up on radar, or maybe even before it pops up on radar, we'll have a better idea what type of storm this is. Is it going to produce perhaps a long track EF5? So my approach is to use computer technology, models, to simulate the storms. So honestly, I don't chase. It's not like something I do. I have nothing against chasing. I think it's great hobby. My research, however, is in the realm of simulation. And in meteorology in general, you'll see there's 3 different ways to study anything in meteorology. You've got observations, theory, which has all lovely mathematics and stuff in it, and physics, and then modeling. And you'll find that in many different scientific fields. Computer models are a very nice tool for understanding what's going on. And until recently, so I've been using supercomputers pretty much ever since I was in graduate school. Over time, as you all know, we have these wonderful little computers in our pockets now, these magical cell phones that are just, incredible when you think back 10, 20 years that we had this technology. Well, the same types of advances have been going on with supercomputing technology. Now, supercomputers are essentially just, in these buildings that are cool, that are just racks and racks and racks of interconnected computers, very fast interconnects. We've gotten to the point now where we can do simulations at resolutions where you can actually get something that looks pretty good. Resolution is a measure of how fine-grained your simulation is. The higher the resolution, the more detail and the smaller structures you should be able to actually resolve. And believe me, at least in the simulation, the tornado is forming before or after, following a lot of other smaller scale things that you might not actually see in the field, unless you had very good observational technology. So, 3 approaches: observation, theory, and modeling. Radar is a wonderful thing. This is a WSR-8AD radar. Inside of this thing that looks like a ping pong ball is a radar. It spins around. It's always operating. All of the federal government puts them out there. It covers most of the country. This is what is the source of most of our day-to-day weather radar imagery that you might see on TV. So for instance, I'm sure half the room probably knows which storm this is without even looking at the top report. This is May 3rd, 1999. That was the Moore, Oklahoma tornado, one of the many. If you want to get hit by a tornado, you want to live in Moore, Oklahoma, and Reno, Oklahoma. There's some places where they seem to come more than once. So this is the type of imagery you might get from one of these. Okay, the WSR-8AD. This is a scan of reflectivity. This supercell is pretty close to the radar, so it caught a lot of detail. You can see some of the distinguishing characteristics of this supercell. The hook echo, in this case, this bullet of high reflectivity means there's a lot of debris in the air. The radar is actually picking up debris in the signature because debris will reflect very well. Most of the large hails over here sort of in the forward flank of the storm and the rear flank of the storm. So this is a classic supercell, and this is what this kind of radar will give you. Now there's other kinds of radars as well, the same basic technology, but more in tune for research. So here's an image from Vortex 2. This is a field study a few years ago. The second Vortex verification of the origin of rotation on tornadoes experiment. Wonderful acronym. So this guy right here is the back of the truck. This is the Doppler on wheels. This is the Goshen County tornado that was studied more than any other tornado ever. The whole Vortex team managed to get several different types of instrumentation on this storm. It was the big success from the Vortex 2 field campaign. So here we have a tornado. There's a researcher taking a picture, and this is actually spinning. You just caught it when it's not. But it's scanning either a semicircle or going around and around and scanning the atmosphere. So radar is very, very powerful because it helps us look into the storm without actually being in the storm. It's a form of what we call remote sensing technology in meteorology. So here we have, this is the result of some of that really close to the storm research radar. And this is much higher resolution, so you're seeing a whole lot more detail. Notice this is only 1 kilometer across. And this is the tornado. It's actually scanning the tornado. You see an inflow or a couplet. It's indicating rotational air. I can't tell you exactly where the radar is, but it's going to be along somewhere either over here or over there because you got going away from and towards the radar, a cyclonic tornado. Classic signature. And here is the reflectivity. In fact, this tornado at this time just has a tiny little bit of debris in the center. No reflectivity here, so it's going to be one of those tornadoes you can actually see. There's not a lot of rain around it, but you do see a little hook. This is not to be confused with the hook echo of a supercell. This is so zoomed in, it's like a secondary little circulation. So very nice, you can do that. We've learned a lot from doing this type of work. In situ, I don't speak Latin, but it's basically when you're taking data at the site. Here's a researcher, Tim Samaras, deploying. He's going to deploy one of his devices that is meant to be hit by a tornado and then capture data. This is the StickNet from Texas Tech University. So they go out and they deploy these things. You can see an anemometer, wind vane, pressure sensor, temperature sensor, dew point sensor. So you deploy these out in a row, try to put them in front of whatever you're trying to study. It swoops through, you take data. So in situ data is very useful. And here's a final example. We're actually flying little unmanned aircrafts into, you want to go to meteorology and fly using the Vorticity, right? Who would want to do that? So actually, Adam Houston at the University of Nebraska, I gave a talk there last week with his group. He's one of my collaborators. He's actually working on flying these into regions of supercells where we can detect things that radar can't detect and other in situ instrumentation can't detect. That's the real limitation to observations, is you really can't get really good solid data on things like temperature and moisture in the storm. You can only sample it where the instrumentation is. We don't know how to remotely sense temperature yet, okay? So maybe someday we'll be able to do that. Now, just pause for a moment and be serious. Storm chasing can be dangerous. This is from a Van's article, the American Meteorological Society, written by Josh Woolman. He's probably the premier tornado chaser in the world. He wrote a paper about the May 31st, 2013 El Reno, Oklahoma supercell, which was crazy. It had a 2.6 mile wide tornado, multiple vortices, multiple tornadoes, just everything you could imagine. The storm evolved in an interesting way. The tornado moved in ways people weren't expecting, and a lot of people got caught, including Tim Samaras from that previous image. He died. He and his son and the driver of the car all perished because they got caught by one of these weird little multiple vortices that came around and from a weird direction. People didn't realize that they were inside of a 2.6 mile wide tornado. Mike Madison from the Weather Channel, he and his tornado hunt team, I guess who got one, they got too close, they got tossed around, and there were no fatalities, but there were some injuries. So, I mean, I probably don't need to tell spotters this, but this is, a dangerous thing. Things can happen. And of course, we've got photography, videography. So what I'll show you next is a little bit of storm chaser footage from Dr. Bruce Lee, who's also one of my collaborators. He and his partner were on this storm, and this is from the Pilger, Nebraska storm. This one little slide is to say, videography, photography. You can get a lot of that just going on the internet, right? That's just from Google. 423, 2 tornadoes. So this was two tornadoes on the ground at the same time. One over here is over this side. This one here is really close. Pretty intense tornado on the surface. So this is the kind of tornado I'm interested in. This was an EF4. Quite intense. So there's a lot of detail in this kind of video, but it's of moderate use.
So, ground debris on the old one, but this one to the south really took over.
So this is the Pilger event from a couple years back. Two very strong tornadoes on the ground at the same time. Very rare for that to happen. And there were 3 fatalities. The small town of Pilger got hit, but Just that kind of storm, so the bigger, more long-lived tornadoes. It's really important, from my perspective as a sort of a theoretician slash modeler, that I don't live in my own little world where I don't pay attention to what's going on in the real atmosphere. And that's something you have to be careful about, because the Mother Nature knows how all this stuff works. The modeling you might know, but we humans are a little slower. Okay, so theory, the theoretical aspect, I'll just say a few words about that. If you're a meteorology major, I know I've talked to a couple of students and such, you know that you have to take 3 semesters of calculus, differential equations, statistics, physics, lots and lots of stuff. It's just about as difficult as an engineering degree as far as coursework is concerned, because it's fluid. It's the nature of fluid flow. It's just difficult. There's a lot of mathematics and physics involved, and the way that we can quantify that is through calculus and things like that. So some people will take this approach and just do theoretical things. So I just scanned from a journal article from Brian Davies Jones. He writes papers that I'm not sure many people understand. There's a whole lot of very high-level math. This is just an approach. They're looking at a specific type of theoretical vortex, looking at how it propagates and stuff. And this is the kind of thing that if you want to understand, theoreticians take this path, but nobody gets away with the meteorology degree without taking some math. It's just not going to happen. Model. So now I'm sort of getting into the part of the talk where I'm going to start showing you some of my research, but a model is sort of a computer program that basically realizes or solves this equation set. All these fundamental laws can be programmed into a computer and be used to forecast the future state of the atmosphere. I mean, you know that we use weather models all the time now, right? How many days ago did we first hear about this giant snowstorm that's forming in the plains? Several days ago, I was talking about this storm that is still developing, right? And we're really good at predicting than we used to be. That's the same kind of computer model. It's using the laws of physics and taking observational data and integrating forward in time. We can do the same thing with research models to study individual phenomena. So some of the pioneering work on this was done right here in Madison. Robert Schlesinger, at the time Department of Meteorology, he was one of the pioneers. He wrote a 3-dimensional cloud model that shows that third dimension that Kerry was talking about that's so important, the vertical component. He's actually modeled supercell, all of basically the gross features of supercells came out in his model. At the same time, another Bob Wilhelmsen at the University of Illinois, who's still a collaborator of mine, even though he's mostly retired, he also did some groundbreaking work. So this is back in the late 70s, early 80s when this work started. So here's a little snapshot from an Emmy Award nominated, not winner, clip that Wilhelmsen and his group put out. It's a little difficult to see, but he's showing the cloud isosurface as a transparent field. So this is like overshooting top, backsheared anvil. This is the rear flank of the snow where the anvil goes, and a few stream tubes showing where the air goes. And that was like bleeding edge in like 1990 or so when he published that. And this is an image that I made from the simulation I'm going to talk about. It's not showing up so good on the screen, but there's a tornado in there. You barely see it. And one of the reasons I like pictures like this is showing the full model domain. I'll talk about models a little bit more. You have to actually resolve that little thing that barely fills a pixel on the screen enough to actually do something useful. And that's why it takes supercomputers, because you have this tiny thing, compared to the 120 kilometers or so on the side, the boxes, and you have to basically resolve all of it. So, if you decide after this talk you want to do this, what do you need? You go to the store and make a laundry list. Here's your laundry list, but I wouldn't get too carried away. You need a model first, okay? Just a piece of computer code that you can run. Now, you can actually download a model that I use for free. Okay, so all right, we got one. You need a good set of initial conditions. Now, that's a little tougher unless you're a meteorologist, but it's basically the adage of garbage in, garbage out. If you feed a model bad data, you're going to get a bad result, unless you're really lucky for the wrong reasons. So you need to have a good set of initial conditions. The storm that I'm simulating is essentially sampled from an actual storm that happened on May 24th, 2011. Using, if you're a modeler, it's RUC data. So it's another model that ingests observations really quickly. Essentially, we tried to sample the atmosphere of the storm and use that for the model, and it worked. It was like the 23rd thing I tried, but it finally worked. This is the part that's probably going to give some of these problems. You need a really big computer. We're talking hundreds of millions of dollars worth of computer technology for the Blue Water supercomputer, which is at the University of Illinois. You have to actually write grant proposals to get access to it because you have to basically show that your model is worthy of their wonderful hardware, and it is great hardware. And you need some luck because just like the real atmosphere, it's hard to predict, and when you run simulations of supercells, 99% of the time you don't get a EF5 tornado, but we managed to hit the jackpot. So a couple of just technical things before I start into the video. So if you're wondering, how much memory the simulation was or how much data it would take, this is just some rough data. So a couple of 100 terabytes of data written out by the model interface. And it took about 10 terabytes of memory to simulate it. Okay? I'm doing an even bigger simulation now. I'm going to show you this at the end of the talk, which is really cool, which is about 40 terabytes of memory in the machine and about a petabyte of data on this. Now, a petabyte is 1,000 terabytes, and a terabyte is 1,000 gigabytes. So you start getting used to peta things, because petabytes are coming. In fact, the supercomputer itself has about 20 petabytes of disk space on it. So it's a big problem. Now, for the rest of the talk, I'm going to talk about the specific research that I'm doing. This work, I want to make sure that I give credit to my collaborators, so Dr. Robert Wilhelmsen, Dr. Bruce Lee, Catherine Finley, and Adam Houston. You might know these folks, they're at research institutions. So what I'm going to show you is a supercell that produces a tornado that's quote unquote on the ground. Of course, the ground is modeled, but is in existence for almost 2 hours. Now, the actual 24 May 2011 storm was on the ground for about that time. The paths were about the same. That was actually very gratifying that we got that kind of result. A lot of the animations I'll show you are looking at things like vorticity, which is something you can't see with your eyes. It's the spin of the air and the shear of the air. Tornadoes, if you're trying to look for tornadoes with vorticity, it's a good field to use because tornadoes rotate so quickly. We've identified in the model a couple of things. First, there's a lot of little small spinning vortices, little whirls of air that happen before the tornado forms that I think are sort of coming together and we're getting some consolidation of vorticity that helps form the tornado. But there's a lot more going on as well. We've identified a feature we're calling the Streamwise vorticity current that is essentially the storm is pulling in air from the forward flank of the storm that's been cooled by the precipitation of the storm right along where the storm air meets the environmental air, which is warm and moist. So you have warm, moist air adjacent to cooler, moist air, and that causes rotation in the horizontal. Okay, you pick the theory on this. When you have these horizontal gradients of buoyancy, it indicates vorticity, but it's horizontal vorticity. Well, this SVC thing seems to get tilted into the mesocycle and become vertical vorticity, which is spinning this way. So this is something we see, it's a persistent feature in the simulation, and we think that it's important. So from here on out, I'll be showing you mostly volume rendered data. Volume rendering is a technique for taking digital floating point data and representing it. Clouds volume render nicely. They look kind of cloud-like. There's several different techniques you can use, but this little sequence here kind of gives you a sense of the scale. So this is the model domain. It's 120 kilometers on a side and 20 kilometers in height. So if you're thinking physically, what is this model? What is its little world, its universe? This is its universe. And the trick we do in this case is we move the box with the storm, so the storm stays centered in the middle of the box where it's far away from the boundaries, which, remember, on the outside of this box is undefined as far as the model is concerned. So I'll zoom in a bit to give you a sense of the scale. Again, that little tiny thing there is where I'm focusing most of my attention, but look at this huge mesocycle, and look at this overshooting top, look at the anvil, you can see Madison-like features in the clouds. So this is all done on computers, okay? But we use observations to help sort of define the environment. And this is in about 60 times real time, showing you the evolution of the storm, and there's a tornado. It descends to the ground, just like we typically see in the sky. But what we'll show when I look at the vorticity field, we'll notice that even though the condensation funnel is descending downward with your eyes, there's already a vortex there, okay? It's already anchored on the ground. And we'll just let this go. So this is the forward flank of the storm. This is what you might call a tail cloud. This is the rear flank. You saw a little sheet of precipitation around the tornado. Again, this is going faster. It's like your finger's on the fast forward button, but so the tornado wiggles around a bit. But yeah, I mean, this looks pretty good. I mean, you look at footage, obviously you can tell it's a computer simulation, but there's enough things going on here that the rain shafts look about right. You see these kind of bursts of rain falling. and this thing goes and goes and goes and goes. So, and FYI, well, I have put a lot of stuff on. I'll give you a web link at the end of the talk, but you can download a lot of my videos from there or watch them on YouTube. But you can see, and now this is cool. You notice how it's wrapped in rain now? That's cool from the perspective of that's what we see in nature sometimes. But if you're on a storm like that, that's a very dangerous situation to be in. If you're chasing a storm and you're coming, maybe you're punching the cord against something you shouldn't, and suddenly you see something like that, and you're not quite sure if it's there, if it's just a rain shaft, well, you're probably too close. So this perspective is sort of from the rear flank perspective in front of us, so I'm just trying to look through the rain. I just wanted to see if I could give an image. There's a burst of rain. Oh, tornado's gone. No, it's not. It's still there. So, I mean, anyone who chases, you know what I'm talking about, right? It's conditions can change very quickly, and if you don't know where you are in the storm, or if the storm is cycling, or you have a new storm popping up, things can catch up with you. You know. Okay, so that was of the cloud and rain field. Okay, so now I'm going to look at what's called the vorticity field. So vorticity is the curl of the wind vector. Essentially, rotation is a good way to think about it. So I'm looking at the red guys here. You're going to see red guys and blue guys, basically. If they're red, that means they're rotating the way we'd expect a tornado to rotate in the northern hemisphere, counterclockwise or cyclonically. The blue guys are rotating clockwise or anticyclonically. And one of the interesting results in the simulation is it also produces an anticyclonic tornado. Now, I was a little nervous about that because they're pretty rare, but it turns out that, and there's just a paper that came out, Howie Bluestein and his team, that, you know, they're rare, but they're certainly not unprecedented. And the anticyclonic tornado that forms in this storm formed right where it should. So this is becoming an anticyclonic tornado. This is going to be the actual tornado. Notice the vorticity field. I'll be pausing again. So notice how you see all this kind of stuff going on. This is the forward flank of the storm. This blue field is the buoyancy field. So it's how cold the air is near the surface. So this is the rear flank, gust front, the boundary, the rear flank, gust front, forward flank, rear flank. Okay, so these are your boundaries. There's that little point where they meet, and there's the tornado forming. So things are forming where they should, but you see a lot of variation in the colors here. So the cold pool, which is this thing that meteorologists refer to as the cold air that the storm produces itself through thermodynamic processes, is very complex. And it turns out that most of the air, at least in the simulation, that fills the tornado comes from very near the ground. So we need to pay attention to what's going on in the ground. But one interesting thing is you'll notice the tornado is already kind of forming, but there's no condensation funnel. And then the condensation, so these are happening at the same time, just the same view as before. But notice that is already anchored in place. So this tells me something. If you can detect this sort of thing on radar and you know it's a big tornado is coming, you could actually maybe increase your warning time. So blue guy, red guy, and you'll notice a whole bunch of things going on right along this boundary here. You see those little red guys? Those are those so-called invisible whirls I was talking about. It seems that a lot of vorticity is consolidating into forming this tornado, but there's a lot more going on than that. You'll notice that it's kind of hard to see when it's fast like this, but there's two twin rotating vortices in this tornado. It's called a two-cell tornado. And I'll pause and you'll see it a little better. So you'll notice that, you can sort of see it here, it looks like a candy cane, sort of. So you have two vortices spinning sort of around each other like a downdraft in the center of the tornado. That's called a two-cell tornado model. And I say model because much of the work on tornadoes has been done in chambers, or models of chambers. And this kind of flow feature has been seen in these high-resolution models. I don't think it's ever been seen before in a full cloud resolving model. So it's good that that's showing up in this because we think it's actually happening in the model. It's probably happening in the atmosphere, but it's very difficult to detect. I was looking at some of the footage from some chasers of the Fairdale tornado from last year in Illinois, and looking for these, you see these little features where you see horizontally oriented clouds. So this is an example. You see a lot of little pieces of spaghetti that are getting twisted around, and sometimes they show up in the cloud field and you can actually see them. But the vorticity field, this is something you don't see with your eyes, but notice all that activity that's going on. All those vortices, how they interact, a lot of it looks chaotic. Some of it looks kind of like there's a nice solid steady state going on, but a lot of it is very sporadic. And again, this whole simulation has produced enough data to probably keep you busy for 10 years. I don't know. There's a nice event that happens when an anticyclonic vortex interacts with a big tornado and gets pulled upwards. You see those vortices getting pulled upwards. When you look at chaser footage, you'll often see these little clouds that kind of roll up the tornado. I didn't put anything in there in this talk, but it's definitely consistent. The model is consistent with observations, which is good. So, and one interesting thing that I was talking earlier about this, the rear flank of the storm often produces warm downdrafts. They're not always cold, and to a meteorologist this is important. Its significance in the whole context of this storm is still unknown to me, but we're seeing some nice variability in the cold, cool temperatures that we think are physically realistic. So when you see like reddish colors here, that's air that's it's positively buoyant. It's actually lighter than the surrounding environment. But anyway, it goes on and on. So this is a two-dimensional look at this particular storm. As Gary said earlier, a lot of the times we meteorologists are looking at two-dimensional pieces. We look at the 850, we look at the 500, 300, we look at these different surfaces. This is the surface of the earth, of the model, so the ground. So this is a view that most meteorologists would be comfortable with. So this is the developing tornado. This is the anticyclonic one. Notice it's blue. And look at all these little guys. And look at this, what's going on here. So this is where I'm focusing a lot of my attention in the simulation, what's going on in this region here. So I'll just let this play, and maybe somebody in the room will tell me what's going on. We can solve this problem together. But in all seriousness, there's just a lot of detail. I think this detail is actually, we finally reached the threshold where we're getting the detail done right enough that we're getting the larger tornado done right enough. Because look at the tornado. I mean, it's bigger. This is just the vorticity field, but it's not like it's just a little dot or a bullseye. There's several pixels or several grid points, dozens of them, that are on this tornado. So it's being resolved relatively well. So the blues are anticyclonic. So one question we have in this research is how come all this air that's rotating in the wrong direction, so to speak, is still sustaining this tornado, which means there's got to be things going on aloft in the storm that are equally important, if not more important, than the surface. Sometimes the surface calms down a bit. You don't see so much chaos. Like in the rear flank, you see tons of these downdrafts and all sorts of turbulence. And in the forward flank, you see some of it, but it's more organized, and it seems to all just be going, getting consolidating. And remember, there's this monster, really strong updraft parked right over this tornado, and it's helping maintain it. But just about anything that gets under that updraft is going to go up because it's so strong. Even near the ground, you've got velocities that are like 10, 20, 30 miles an hour, only like 50 meters above the ground. So really strong updraft. And that's an important result as well, because some scientists don't believe that you can form tornadoes, with just having a strong updraft. And they're probably right. It's just that that strong updraft is a key component to maintaining the tornado. And yeah, other things have to happen as well. If you have a weak updraft, you're probably not going to get something so strong. So this just goes on and on. There's another blast in there. This is one of my favorite sequences. So this is just looking down the forward flank downdraft on where you're dropping parcels there. And there's our tornado going nuts. And here's this feature we're calling the Streamwise vorticity curve. We think we're onto something here. So this is horizontal vorticity. It's kind of rotating like this, and then it's being sort of making this inflection point and going up. We'll show it one more time. And so now you have horizontal vorticity becoming vertical. And vertical vorticity is what tornadoes are all about, right? How do you get all that vertical vorticity going? And we think this is actually probably not driving the tornado itself, but it's probably doing something to maintain the mesocyclone. So this, this is like 500, I don't know, maybe a kilometer across or so. So this is something that it just kind of wraps into the mesocyclone, but it's actually a kilometer or so away from the tornado. So I'm certainly not claiming that this SVC thing that we've identified is the tornado, but we think it's helping to maintain the storm in some way that is helping to allow this tornado to happen. So here's another sequence that shows this storm in just beautiful, stunning detail from a scientist at NCSA who does computer graphics work, David Bach. So this is showing you the mesh, basically. It's a stretch mesh, but we parked the storm right here. So we're looking at it from above. There's the overshooting top. He's going to tilt the box, and I'll just let this play and shut up for a few minutes. So these look a lot like Madison clouds up here, don't they? Watch this animate, and you tell me. So what I did is I said, David, here's my data. You make a picture of it. You make a movie. And he took his code, and he made this stunning rendering of this stuff. I've never seen anything so good before. So this is all in the computer, right? It's all on the computer. But if you sort of fuzz your eyes out or take your glasses off, you might almost think you're looking at a real storm. We're getting closer and closer to that. And now, this is beautiful, but where's the science, right? I mean, it's beautiful, it's showing that this model's probably doing a good job. And this online, you'll see, the detail isn't as good when you're up on the screen. But so then here's just some stuff I did. Let's just drop some parcels. So if you're looking at a supercell, you'll see the cloud, but what's going on inside that cloud is complex. Giant monster updraft. Here's basically where the SVC is, and here's our tornado, of course, just churning along. So once I got the simulation to actually happen, I took all these tools I've been developing over the last decade and then threw them at this. You know, I was waiting for the simulation, but I had most of the graphical tools were in place, but I just needed the simulation. So just when we were running out of computing time on the machine, this happened, and then we got some more time. So we were able to keep the research going. But that's a common story in research. So, you know, there's just lots of interesting things going on here. At this stage in the game, we're just trying to get our hands around this thing because it's no one's ever really done this before. So when you got some new research, you got to sort of, what do we look at? What are we gonna try to do here? Here I'm dropping parcels in the forward flank. Those are the blue ones along the SVC, the red ones, and generally in the RFD region of the storm to show that the air comes from different. You know, what's going on? If you try to develop a conceptual model here. One thing that's interesting to me, at least, is all the air in the tornado is coming from the cold side. So the tornado is actually made up of air that has been cooled more than the surrounding environment. It's harder to lift dense cold things than it is to lift warm things. But when you've got an updraft with instantaneous velocities of over 300 miles an hour aloft, chances are you can lift some cool air. And the red here would sort of indicate what we're calling the SVC. So again, trying to figure out what's going on. And the rear flank gut front, you notice how the parcels are kind of just rising upwards. That's very consistent with observations as well. So part of this is just fun. You know, research is hard, but it's also fun. And especially when you have a really cool project like this. So we're hoping that down the road, this kind of work will eventually find its way into helping do better predictions. Now here's sort of coming into my talk now. This is from a simulation that's at 20 meters. And so it's the highest resolution simulation I've ever done. And I use the same environment, a few different tweaks on some parameters, but it's basically the same environment. And here's the cloud field, and don't worry about the ground, it's the buoyancy field, but you really can't tell because the angle is like standing on the ground. So, what do you know? This is actually an anticyclonic tornado. And it's a tornado, and it's got tornado strength winds to the ground. Here is your, like, what we would consider to be the wall cloud, and it is your tail cloud. So, but if you think this guy's interesting, just wait a few minutes and see what happens after that. And I'll be comparing to some videography as well. So it's turning along. Now we have the cyclonic. The anticyclonic guy went away, and this guy really rapidly becomes an EF5. Notice now we're starting to see some detail that you see in some of this great videography, where you see like evidence of maybe multiple vortices or you know, little horizontally oriented rolls that are being infected around the tornado. It also becomes rain wrapped at times. The RFD air is kicking out all these downdrafts. Some of them are rainy, but this actually looks kind of like a real tornado. Looks like Fairdale a little bit, maybe, if you use your imagination. In fact, I'll be comparing just to sort of do a side-by-side of Fairdale, a couple of different perspectives. And if you've been looking at some of the video rolling out front, you've already seen some of it. And again, this is running way fast, but this guy got stuck on the side of the road on I-39. He shouldn't have been there. We can argue about that, but I'm just trying to sort of compare. I've slowed this down so it's more like in real time. But, you know, look, you'll see it. It's hard to see on the screen, but every once in a while you'll see a little bit of daylight in between. You're actually seeing some of the multiple vortices in this. There's one right there. And you're kind of seeing the same thing in the simulation. Again, this is a different storm than I'm simulating. Now, this one is this poor guy who's just stuck in his house. He's filming it. It destroyed his house. He survived. His wife did not. His camera did. This is obviously something you don't ever want to do. But again, footage like this, where you can see what's going on up close, actually has some scientific value. And I'm only going to run this until for a few minutes. If you see this whole thing, you know what's going to happen. But yeah, very. And I stop it there. I don't want to. It continues to record, and you can hear the house collapse and stuff. But it's all right. Now I show that for two reasons. One, it's to to show how dangerous these storms are. But two, and I would never encourage anyone ever to go get this close to a storm. There is potentially some scientific data that can be taken out of some of these videos, at least trying to trace and see what the multiple vortices are doing or whatnot. But again, this is, be very careful if you're chasing. And to sort of close things off, here's the vorticity field of the 20-meter simulation, which gives your anticyclonic blue guy that's kind of churning along. But watch what happens shortly. When suddenly you start to see a bunch of reds and yellows. So this is anticyclonic vorticity and cyclonic, and then suddenly, I'm not sure what's going on, but now we have an EFI. And this guy is going to grow, it's going to strengthen, you're going to see all sorts of cool stuff going on, and you will also see the multiple vortices near the surface. And again, I'll put this online. You can slow it down because it's going so fast, it's hard to really see what's going on, but you get the general picture. Now you see definitely the two-cell structure where you see two intertwined vortices. This is now in very sharp focus. It really wasn't in the lower resolution simulation. And it goes on. And there's just so much to do. There's so much to look at and to try to understand from just a single simulation. But of course, and it gets wider, the swirl ratio increases, it gets wider, it gets multiple vortex, and then you see more of some of these mergers, and then the tornado widens and the average wind speed weakens. The circulation, if you're looking at that, is probably consistent, changing, but look at those horizontal guys. There's some really cool horizontally oriented vortices that go nuts. Oh, my closing slide's been zoomed at the end, sorry. This is the problem with videos for talks. But I wanted to sort of close up. But anyway, so yeah, this is online too. But isn't that cool? I mean, let's just call it cool. So anyway, this is computers can do this now. This isn't something that was really feasible up until just a few years ago. Just to sort of summarize, first, thank you all for coming. I hope you've enjoyed this. We still have a lot to do to learn about supercells before we can do something like predict an EF5 tornado, say a day in advance, or maybe even a couple hours in advance. We're not there yet. I don't know if we'll get there, to be quite honest. Louis Michelini, who's a director of Weather Service, he's an alumnus. He just was given a reward at UW campus. And the reason I mentioned it is he was talking about back in the 70s when he was doing research on cyclones, low pressure systems, how he never ever imagined we'd be able to do things like forecast the existence of a giant snowstorm 5 days in advance, 6 days in advance. We're getting better at that, but we have tons more work to do. I'm not just saying that for the grant funding. All the scientists, the general meme about scientists and grant funding right now. Anyway, no, we really do. So we're doing a lot of good work observationally and also numerically. I'm hoping that my own research eventually, way down the road, will help guide observational work so that we can actually find these features in the real atmosphere. And again, I say thank you to you spotters. You do a very crucial thing that's very important. Thank you for what you do, but please be careful. And thank you for your time, and I'll take any questions.
Is it nice to have somebody who enjoys his job as much as Dr. Orff does? That's some incredible video.
Fun stuff.
And I remember when I first got interested in meteorology, there were still a number of meteorologists who thought tornado wind speeds were near sonic strength because that's what accounted for the roaring sound. Right. All these things that we've been able to disprove over the years, and then things that we are able to prove, and especially when you can simulate them in the model world and compare that to the real world, that's where the science of meteorology is going. And that is just unbelievable, some of the things that we're starting to learn through somebody like Dr. Orff's research. So, any questions at all?
You want to take over here? I'll let you.
Yeah. Chad, go ahead.
Yeah, I have a question. It just looked like to me that that one Streamwise video and the rotation there looked very similar to some rotating inflow bands that I see. Is that what you think that probably is the inflow of the thunderstorm? And is it more surface based than that?
It's okay. So the SVC originates, I would say, near the ground up till say like 500 meters. So it's near the ground.
Okay.
So an inflow band might typically be referenced to something that's coming from the warm side of the storm, but this is an inflow into the storm on the cold side.
Oh, that was from the cold side.
It's from the cold side. That's what is interesting because again, it's generally hard to lift anything, right? Dense air, cold air is dense and harder to lift, but the updraft is so strong, it's able to do that. And also, it's the boundary between that cool air and the warm air that produces that rotation in the first place. So we need to have this baroclinic zone, this region where you have horizontal vorticity generated, and then it gets tilted. And that mechanism has been known about for a long time, but it really shows out clearly in this simulation.
Very good, thank you.
Do you have a sense from your research of how much variance the wind is within a tornado vortex? Because they're rated EF 1, 2, 3, 4. So you think, well, this is 150 mile an hour.
Right. Well, the way the EF scale is used is it's used using damage indicators.
Right.
So it's not supposed to be a measure of wind speed. And I've been a little fast and loose when I say EF5 tornado because technically you can't have an EF5 tornado in a computer because there's no damage, right? But the winds are EF5 strength. Variation, yeah. So when a tornado is rated, if a tornado is an EF0 and then ramps up to an EF3 and then dies, it's an EF3 tornado. That's how they're classified. So it's the fastest wind that is occurring that defines the damage thing. So yeah, there's a lot of variation. You can see it in the simulation. You can see that some of these vortices, you see this in real damage where a house is destroyed and a neighbor or two neighbors down isn't touched. Probably because one of these vortices is about 50 meters across, very intense. It's moving quickly, so it's translating, it's rotating and moving fast. And when you have those two things added together, you get these really strong winds. So there's a lot of variation in these big multi-vortex tornadoes. Weaker, shorter-lived tornadoes, probably not as much variation. It's probably much more smooth and less weird stuff going on. But there is a lot of variation, definitely.
So with the S species that you talked about, how does that correlate with the ghost train they talk about in the slider trains? With the chasers seeing the ghost train behind the
ghost train. Yes, I've seen, again, so we have all this cool jargon and the ghost train. If I'm thinking of, it's sort of like, it's a cloudy thing, a misty thing that's kind of coming, it's something you see, right? Mm-hmm. It's on the cold side, it's coming in.
Yep.
Yeah, I've seen, with reference to maybe the May 31 storm, yeah, I mean, you call it what you want, but this SVC thing, or air coming in, and you saw it in I won't show it again, but the time-lapse photography of the supercell, where you see that stuff coming in from the forward flank, and that is probably the ghost train or maybe something like it. The inflow speeds going into that tornado are tornado strength. I mean, you have winds that are EF0 strength on the ground straight line, just being sucked in by that strong updraft. So yeah, you're probably hearing that, right? That steady inflow, and it's got rain in it, and maybe some hail. So yeah, it probably makes a funny noise. And, that's a good term. I like that term. Ghost train. Very scary. Any other questions?
Hi, it's Derek from UW. Two questions. From everything I've seen, including these simulations, it suggests that all large tornadoes are multiple vortex tornadoes.
I would agree with that.
Is it fair to say that?
I think so. I've heard David Llewellyn say that, and he's like a tornado modeler. He thinks almost all tornadoes that last long enough and are big enough for multiple vortex.
And that has implications from a chasing perspective. With these vortices can spin off sometimes, and people who are very close can be caught in those. Obviously, we've seen some tragic results of that. My other question is, your simulations here are very indicative of a lot of model research like this, and that you're showing things we've never seen.
Yeah.
And we can actually, with current technology, even observe.
Right.
So I wonder what thought has been given to how we might employ strategies for observing these things that are in these model simulations.
Excellent question. Something that's on my mind.
Right? Because radars need targets to observe these things.
Exactly. So that's an excellent question, and it's something that I want to say keeps me awake at night. But as a modeler, when you see something in your model and it hasn't been seen in the atmosphere, then you need to go find it, right? But on the same token, when you see something in the atmosphere that people don't understand, you have to find a theory for it. So there's this nice push-pull or parallel paths with this. So I have just started thinking about this. Maybe RHI scans on the forward flank, okay? Because the SVC is doing this. First it's like this, and then it's like this. Nothing is straight up and down, or it's all tilted. So maybe if you were able to go on the forward flank of the storm and do RHI scans, where they each go up and down, and with several of them, you might be able to pick up some of this. That's one thing. Some of the UAV work, the unmanned aircraft, could be playing around there to see if those vortices are there. Good old radar works as well, but you have to have scatters, and sometimes you don't have scatters in that region, so you're not going to see stuff. So that's a great question. It's something I'm already talking to with my collaborators who are more field-based. And do you have any suggestions?
Well, I was just going to mention the idea that you employ tracers in the model to trace out the flow.
Yep.
I was thinking of something like chaff, where you could deploy chaff in some way that would provide the tracers that you need.
And then you could trace them with radar. Yeah, that's an interesting idea. Very interesting.
So you're saying that if a large tornado runs a multiple vortex, then to get that you have to have vortex breakdowns.
Right.
So how does the vortex start if it isn't already?
It starts as a single tornado, yes. That's a good clarification to make. I think, yes, these big high-end events are multiple vortex. They don't start out multiple vortex. And that's his point. He's right. If you look back to the beginning of either of these tornadoes, I'll do the last one first because it's right here. Notice see how it starts out? This is a single cell tornado at this point. A single cell tornado has an updraft everywhere. Okay, so it's basically embedded within an updraft and it's rotating very quickly. What happens is over time, and the physical reasons for this, we talked about swirl ratio increasing, etc. That's definitely what's going on. But why? And that's the question we're trying to figure out. This thing is full of rain, it's getting cold air in it. Now you can see, so this beautiful example of the 2-cell model and how we have vortex breakdown going on. It hasn't made it to the ground yet, but anyway, yes, my belief, based on science, is that these larger tornadoes, these stronger and higher end tornadoes, are multiple vortex, just about every single one of them. But they probably didn't start out that way. But again, this is just a simulation, and I'm a little hesitant to make any grand conclusions about a single simulation.
Yeah, I'm okay with saying that they eventually become that way because I don't.
They don't start that way. No, you're never just going to see a giant wedge go. If you have, I'd like to see the footage. And I hope it doesn't happen for everyone's sake. I mean, Joplin was probably as good an example as anything. In a weird, where you get an FBF5 pretty quickly, it does its thing and goes away. But no, I would say, who knows? Mother Nature does all sorts of things. Sometimes it looks as if the dang weather cyclone just descends to the ground, right? So what is that, right? Some of these big wide tornadoes, like 31 May, you could sit and navel gaze about it. Is it a tornado or is it a mesocyclone on the ground with embedded tornadoes? Are those multiple vortices or multiple tornadoes? You have satellite tornadoes around multiple vortices. It's just, so yeah, with high swirl ratio, things go crazy, definitely.
And then you have something like Gerald, Texas,
Right.
which is a very small tornado, but I mean, moving very slowly. And
Moving slow, oh yes. When the tornado itself is kind of not moving, what happens is you basically have the balance of forces. The tornado just stays and cranks along, and it can go over one spot repeatedly. It doesn't have to be like a big multiple vortex to kill a lot of people. Yes, high density population areas, even weak tornadoes can cause terrible fatalities.
Well, another tornado that we saw in 2005, August 18th, was the Battery Ammunition Plant tornado. That was not a huge tornado, but it was multiple vortex.
Yep.
So
Yeah, it's hard to say.
And the funnel looked laminar until about 2/3 of the way down, and then
You guys started to do the breakdown. Very good. Yep.
very good.
any other questions? All right.
One minute. Oh, all right. I'll take it offline.
Thank you again. Do you have these online at all?
Yes, I do. Yeah, I put a really easy website, orf.media. Yes, there is a .media prefix. Okay, it's really orf.media. I've put all my talks. This one will find its way online if I can get it to work. So yeah, you can watch it and slow things down. It's hard to see on the screen, but it's 1080p. You can put it on your big TV screen. It's worth it. It's worth it. You want to do
go
this.
out and get a big TV.
That's right.